Hi everyone, today's video is going to cover determining the pH of a weak acid. And before we dive in here, I just would like to go over a few things when it comes to this particular area in chemistry. Typically, it's a spring semester topic, traditionally anyway. We typically study acids and bases and the concept of weak acids and weak bases. We also use the concept of our dissociation constants, our Ka and Kb in that space. And then we also have sort of next door, we have concentration of gases. We look at that in a similar fashion using equilibrium constants. We also look at buffers, okay, acid-base neutralizations, where we may have a strong acid, weak base, or strong base, weak acid, and we need to do some ICE table work. And ICE table simply means the ICE is initial change in equilibrium, and it helps students set up the math, so to speak, in these particular types of questions. We also see it referred to as RICE, and that just means simply listing out the reaction. And it's also sort of a way to stay organized when you're working these problems. And the way you can detect you're going to be using ICE or RICE is that you're given a weak acid. They'll tell you it's a weak acid, or they'll give you the Ka constant or the Kb constant. Keep in mind when you do the pH of an a base, there are a couple things on the back end you need to adjust for. I'm starting you off with simply a weak acid. Acetic acid is very common when you're doing these types of problems. And the questions are pretty basic. They're just saying, okay, take a particular weak acid we have here. We have our Ka value. Give me the pH. And what they're saying is use the equilibrium constant to determine pH using some higher level math here. So I do remember in my days studying chemistry in college, seeing this part, you see all those X's and formulas and ratios. You're thinking, oh, this is giving me a headache, right? But it's actually once you do it a few times, it's pretty straightforward. And again, this is a pretty fundamental type problem here that I'm giving you. They can get a little more complicated. I'll try to get some of those out here in the coming days and weeks as we enter summer of 2026. But I'll go ahead and get started here. Now, I'm taking you systematically, steps 1 through 6, on how to solve these. And I am going to scroll down here. If you give me a moment, the answer is written out in, I typed it out for you. So it's easy to follow on the back end, but I am going to write out the math as well. So I'm going to write it out in the video. You'll have a copy of this in the description box. Just go to the link in the description box and you can go out and see this worksheet for yourself. But let's get started. And by definition, I just wanted to put that out there. The Ka, by definition, is an equilibrium constant, and it's for the dissociation of acid. And we call that in generic terms HA, right? So H is your hydrogen, A is some anion. It could be polyatomic or monatomic. And we're going to put that in water. It'll form its conjugate base, whatever that might be. And we'll say that conjugate base is A minus. And then we have our hydronium ion. And then that's what defines the acid. We're going to take that concentration of our final H plus, or in other words, our H3O plus, our hydronium. That's how it actually exists in these solutions, and we'll determine our pH. So from the top, we're just going to take the weak acid equilibrium equation. And we'll start off with acetic acid here. And I'm going to put R. That's my reaction. So I'm going to use RICE instead of ICE. It's total preference for you all on how you do that. But I'll just go ahead and write out. There's my acetic acid. We're going to drop this in water. You don't always see water listed. It's sort of a shortcut just to remove it. But we do know we're putting this in an aqueous water solution. And yes, water is present. Now, it's a pure substance, so we don't account for its concentration. The concentrations that are changing are, of course, the acetic acid that you drop in, and then its final, we have our final acetate ion and our final H3O concentration, okay? So we're really concerned with acetate. So here's our acetate, okay? And yeah, we're only concerned with these three, really. And I'm going to start with step 2 here. We're going to move into step 2. So we have our reactions. We have our acetic acid, our first formula listed with liquid water. And I'm not putting in the states of matter subscripts, just FYI. And then we have hydronium and acetate as a result. And what we care about here in the end is what's my concentration of H3O plus. All right, so we have initial. All right, so we're starting off with 0.5, or not 0.5, sorry, 0.15 concentration. And everyone else across the board is just 0, right? So before we put this, acetic acid and water, everybody else is 0. We have 0.15 concentration for our acetic acid. We're going to change, right? So our change, and this is where we start putting in our x's here, we're going to add an x for an unknown amount of that concentration that's going to be dissociated in water. And so we say that's minus x, and then we have plus x and plus x over here. So for every acetic acid molecule that goes into water, we'll have one H plus ion and one acetate ion, and that's represented right over here on the right hand side. So it's basically a 1-to-1 ratio. Things can get interesting when we have coefficients out there in our balanced equation and so on, but again, we're keeping this pretty straightforward in this type of problem. Now we have our change. So we've said, okay, we know we have to account for our acetic acid dissociating to some extent. We don't know, it's a mystery. We'll find that out using the Ka, our acid ionization constant. In the end, we'll have equilibrium, and that's sort of our final state. So we have our I, our initial state, our C, which is our change. It's a temporary change. It's going to be dynamic there. And then we'll have a final equilibrium here. So I'm just going to sort of demonstrate the math. And then X and X. So far the math is pretty straightforward. We now have the information to set up our Ka, or acid ionization constant formula, to solve for X. We want to know how much X, or how many H plus ions dissociated in this particular setup, and how much concentration we have of H3O, so we can determine the pH. Ultimately, we just want our H3O. We just have to take several steps to get there. So we'll start off with, we know Ka is pardon me while I'm writing here real quick. Sorry for the silence. So what we're looking at is concentration of products, concentration of reactants. It's a ratio, and this number value is actually, we're given that, right? It's 1.8 times 10 to the negative 5th. So what that tells me is that the concentration of products to reactants is pretty small, right? It's going to be a small amount of dissociation. That's why it's a weak acid. Okay. And from there, we just need to set up our ratio as defined by X, in our ICE table. So products here would be H3O, and our acetate anion on top. And then we have concentration of our single reactant here, right? We have our acetic acid on the left. Now, when we get to, so we're ready to rock and roll. We're ready to do our math and figure out, okay, what is our X value? However, in most cases, we can do a little trick to sort of help the math move along here. And that's in number 4, okay? The approximation where X is dropped from the denominator. So what we're saying here in these cases, most cases, is that the X is so small that it's pretty much close to 0.15 here in this particular case. And I'll show you the math on the back end, because some teachers in college, I would say a good portion of them, make you prove that the value of X, the amount of those H plus cations that dropped in solution, is less than 5%. So we can just ignore it for math purposes, okay? If we left that X in there, we would kind of have a gnarly quadratic equation to break down via calculator or whatever methods that you use for solving quadratic equations. When you have a middle term, we're going to be stuck with a middle term. Okay, so in essence, removing that X at the end, we're going to be left with just X squared equals a number. We square root it, and then we're off to the races. So, but again, I'll prove it via the math here below. So what I'm going to do is I'm just going to get rid of that X, okay? And what we'll end up with is, I'll clean up the math just a bit. Okay, and cross multiply would be a perfect perfect way to solve this. So we have X squared equals, and then whatever the product is of our Ka, 1.8 e to the 5 or e to the negative 5, Angie. And then we get 2.7. And of course, we just need to square root that. So if we square root that in the calculator, I get a, one moment, I get an X value of, I'll use 3 sig figs here. Okay, so X has a value of just over 1/1000th. Okay, pretty tiny, right? And that is representative of our concentration of H3O. And I can go straight from here to my pH and call it good. But the final, yeah, I'm actually skipping ahead here. We'll do number 6, final pH calculation, negative log. We just do negative log of that answer. I get 2.78. I think I might have gotten 2.79 for rounding originally, but yeah, 2.78 is our final pH. That would be our answer to number 6. Now, if we take, for number 5, it says verification that X is less than 5% of original concentration. Well, let's find out what 0.00164 is of 0.15. So if we take 0.00164, I'm guessing it's not going to be greater than we'll do times 100. Okay. So to find percentage, we're just simply going to take the ratio of our X value, 0.00164, divide out by 0.15, and then figure out what that is as a percentage. Yeah, times it by 100. I get just over 1%. I get 1.09%. Okay, so what does that tell you? That simply tells you that the amount of H plus that dissociated from the acetic acid originally is less than 5%. So we can assume that X is so negligible that it's really not going to change the 0.15 concentration. And it'll help us from a math perspective, okay? So in the end, again, we get the concentration to be 0.00164 of our hydronium and our acetate, but again, hydronium lends to pH, and we get a final answer of 2.78 on the pH. Now, I will come out with more questions in this particular area. I just wanted to start off with this first, and I hope this helps. Like and subscribe if you'd like to see more information from me coming out on chemistry, physics, algebra, geometry. Those are my main specialties, you could say, over the years. And then, of course, anatomy and physiology. I announced just recently that I gained my certified coding specialist certification or credential through AHIMA. Very excited about that. I start work at a national hospital system here in the next few weeks. So very excited about that. And just I'm saying that because I'll be putting out anatomy related questions as well and share my thoughts in the health information management industry as I move along with it. And that's it.